Okay, so maybe we can start. Good morning, everyone. I'll replace Professor Knowles for this lecture today. And where we stopped last time was this proposition 18. And Professor Knowles also presented the proof of this. And so these were large deviation bounds, which were expressed in terms of LP bounds on linear combinations, or quadratic bilinear combinations or quadratic combinations of random variables. And today we want to reformulate, or the first thing which we want to do today is to reformulate those bounds in terms of the stochastic domination. That was the sense of high probability estimates which we used all the time also to formulate the local law. And then later we'll start with the proof of the local law actually. Okay, so this we have proven, and from this we want to conclude today corollary 19, which has essentially the same assumptions, or almost the same assumptions. So let xi, yi, and now also the coefficients will be random, ai and bij, but they will at least be independent. So be independent families of random variables. And we just assume that the indices run from I and j run from 1 up to n. And then before we assume that these random variables are independent, so the xi's and the x1 up to xn, y1 up to yn are independent. Suppose that and we assume the same conditions, so that satisfying. So we assume that the expectations of those is 0, and that their moments are bounded. And xi, or the p norms, are bounded. Mu p for all p in n, and yeah, the same for the yi's. And then we have the completely analogous statements here, except that they're in the stochastic domination sense. So first we can look at the linear combination of ai xi, and those will be this linear combination will be stochastically dominated by the following kind of norm on the coefficients. Right, that's somewhat the L2 norm, small L2 norm on the coefficients ai. And now let me point out that now the coefficients here, they're also random. So this here is still a random variable. Okay? And then we have the same in the other two cases. So we have ij, bij, xi, yj is stochastically dominated, while now it's somewhat the Hilbert-Schmidt norm of the matrix B. And then as a third part, we have the same as a quadratic form, but we have to omit the terms where the I is equal to the j. Okay, so let me quickly prove this. In fact, I will only prove the first part because the other parts are all analogous. And for that, I just will use the first part here. So let me record it maybe quickly up here. And then I have to remove this proposition. So we know that the p norm ai xi is bounded by some constant Cp mu p, and then we have the expression we want. Maybe it is here. Okay? But yeah, let me remind you that here the AIs were deterministic, but there's some standard trick from probability theory which will help us here to do it. Okay? Okay, so proof, as I already said, we only prove part I. The others are similar. And yeah, we want to prove a stochastic domination, so we start by fixing an epsilon and a d. And then what we'll have to do is we have to estimate the following probability, namely we have the absolute value of this linear combination, and this we want to compare with the n to the epsilon times, and now we take the right hand side, so that was ai squared sum over I to the 1/2, right? That's the probability we want to control. And now the AIs, they are also random variables, but by assumption the ASIs are all independent of the XIs, so we can we can easily use conditional expectation to somewhat make this here deterministic in the following sense. So we can first just rewrite this probability as an expectation of the conditional probability of this expression when we condition on the coefficients AI. So how does this look like? So we have the same expression here. This is bigger than n to the epsilon, the same as before. And then we condition on the random variables AIs, okay, on all of them. So that means, that means that we can think of them as just being deterministic. And the point here is the laws of the XIs will not have changed by this conditioning because the AIs and the XIs are independent by assumption, right? Okay. Sorry, there's a closing parenthesis missing. And now for this conditional probability, we can now apply this here. So that was the proposition. This is half readable. Proposition 18, the first part. If we would have here a p norm, okay. So, but for this we can just use Chebyshev in this conditional probability. So Chebyshev for the conditional probability. So that's this inequality which relates when you want to estimate the probability of a random variable being bigger than another random variable or than something deterministic, you can just express this in terms of the pieced moment. So we get the following: we have the expectation, and now we have to take the expectation of this random variable to the p. So sum ai xi to the p. But now we work in the probability space where we condition on the AI, so I have to keep the AIs here, right? So that's and then I have to divide by the right hand side here to the power p. So I have an n to the epsilon sum I ai squared 1/2 and the whole denominator to the p. And now we have the piece moment here, or the piece norm, and then we can use this 18 part I, but with a conditional expectation. It's not a problem. I guess you all seen that in probability theory. So now we can use the first part here. So then we can estimate the whole term inside by Cp mu p to the p divided by n epsilon to the p. And yeah, this term here on the right-hand side, this cancels out, right? This is exactly this term to the p. Okay, so that's all that survives. I still have an expectation here, but that's a constant, so that's easy. This expectation is easy to compute. Well, it just expectation of a constant is, of course, the same constant. So this is of order n to the minus d. When I choose the p large enough, and I just have how to have to choose it, just have to choose the p to be bigger than d over epsilon. And well, that was the whole proof. Okay. I hope you're somewhat familiar with this conditional expectation, and somewhat the rule of thumb is that if you condition on something, you can just think of this as a constant, and all probabilistic arguments go through with that. Okay. There are no questions so far. Then I would we continue with the first version of the local law, or which we call weak local law, because the error term will not be as strong as in the version we saw 2 weeks ago. Okay, so that's a new subsection. So section 2.2, weak local law. And yeah, so maybe some explanation. So why is it weak? So it's weak in the following sense. So theorem 11, which was the local law we were working on for the proof, achieves two things which are quite different from each other, or separated. So they are essentially separated, separate things. And these are the following. So first we control or bound the difference between Gij and m to the well, I don't need this, and m, which was the Stieltjes transform of the semicircle, times delta ij on all scales down to n to the minus 1 plus tau. Okay, and then the second part is also that we have optimal error terms, error bounds. And this will actually be very important later when we want to understand the very precise behavior of the eigenvalues. And maybe I just quickly recall what theorem 11 looked like. Well, the most important part, or the part I'm referring to here, was that the Gij is equal to m delta ij plus an error term which was of order, well, how did we write it? I think we had a psi there. Yes. So we had a function psi here, and the psi looked as follows. So while this was uniformly for Z and S, and the psi had the following form. It was the imaginary part of the Stieltjes transform plus 1 over n eta. Okay, so the two things here is, so first of all, if you prove this here with some other error term which might be smaller, which might be bigger, then you already proved A, and then B is just to get this optimal error term here. So this error term here is actually the smallest deterministic error term such a statement can hold. Okay, and now what we first want to do today is we want to focus on this part A, and prove a weaker version of this local law. Okay? And why do we do that? We do that because these parts correspond to separate difficulties. In the proof, this we'll see like in the next few weeks how to treat both of them. Difficulties in the proof. And here we deal with A without B. Okay, and yeah, I want to define some notation. So define lambda as the maximum of the differences here. So I take Gij minus m delta ij absolute value, and then I take the maximum over all matrix entries. And yeah, now two things are very important. So first of all, the lambda is random because the G is random. Note lambda is random, and also G and M depend on Z, so it also depends on Z. It depends on Z. Okay, and then we have the following statement about this lambda, which is then this weak local law I was talking about. The following proposition, proposition 20. This is weak local law. And what does it say? Well, lambda is stochastically dominated by n times eta to the minus 1/4. And this holds uniformly for Z and S. Okay, so that's a statement of this type, right? We compare. So we compare the Gij and the M delta Ij for all Z and S. So that's that's what we would call a local law, and it's a weak local law because you can see. I guess it's easy. You can easily convince yourself that this error term, this n to the n times eta to the minus 1/4, is much bigger than this error term here in general. Okay, and the rest of this section is devoted to the proof of proposition 20, and then the step B we will later address. So then once we have this kind of weak error bound one, there are certain techniques to improve this error term to get the optimal error term in theorem 11. Okay, so proof is the rest of the section. And well, we define a little bit more notation, namely we have a lambda star, which are just the off-diagonal terms. So this statement here says that, well, the off-diagonal terms, there the delta Ij is 0. So that means the off-diagonal terms are small if the lambda is small. And the lambda star just expresses this. So the lambda star is just the maximum over off-diagonal terms. Then we need a theta, which is the G minus M. Right? So the G was the Stieltjes transform of the empirical spectral measure, which is just the normalized trace of our resolvent big G. And then we need a psi theta, which looks as follows. It's im m plus theta divided by n eta, and then you take a square root. And actually later it will turn out that this theta is actually is of size 1 over square root n eta, and then you get the theta. You get the, from the psi theta you get the psi back. Okay, and the starting point of all of the following analysis is Schur's complement formula. Starting point of the proof of proposition 20 is Schur's complement formula, right, which we, for example, stated in the proof of lemma 16, and we also, we'll also look at it in the exercise session today. And from Schur's complement formula, we can conclude the following, namely that so what is missing somehow in this analysis, so what we want to prove is that the off-diagonal terms are small, but for the diagonal terms you have somewhat more complicated behavior, right? You want to prove that the diagonal terms here are close to m if the lambda is small. So we somewhat need some extra information about the diagonal terms, and that comes from Schur's complement formula, which one can write as follows. So if I look at the II diagonal entry of the resolvent, I take the inverse of this, then I get that it's HII minus Z minus, and then I get the following sum, KL without I, and then following combination HIK GKL I HLI. Okay, and this formula we want to refer to a few times, so that's what I will call star. Stick to round brackets. Okay, and now maybe you remember that for the Stieltjes transform, so for the little m, for the Stieltjes transform of the semicircle, we had somewhat a very similar equation, namely it looked like this. So we had 1 over m is equal to minus z minus m, right? So that, well, if you look at it from very far, then these equations look already somewhat similar. And in the next lemma, we want to bring this equation into a form which looks somewhat more like this, but of course you will have an error term here. And then the goal will be to prove that this error term is small, and then we can provide it, since this equation has only a unique solution, which is also stable in the sense that if you perturb this equation a little bit, you get something which is close to m, and from this, using that the error term is small, we will then conclude that the m is that the GII is close to m. Okay, and the first step for this will be the following lemma, which somewhat identifies the error term in this setup. Okay, that's lemma 21. That's the following. So 1 over GII is equal to minus Z minus G plus YI, which will turn out to be an error term. And the YI has the following structure. So YI HII. So this we already know by some examples or some homework, that this will be small, right? This will be stochastically dominated by n to the minus 1/2. Then we have an error term AI, which I'll define next, and another term ZI, which I'll also introduce. So AI is defined as follows. It's 1 over n sum over k. Then I have the following combination, GIK, GKI divided by GII. And then there's only the z missing, and the z looks as follows. It's 1 minus the conditional expectation applied to the term which we had here on the right-hand side. Okay. So HIK without I. GKLI HLI. Okay, and maybe just recall what the PI was. Well, I guess it will also appear in the following. So the PI was the conditional expectation when I freeze everything that's not in the ith row or column of the random matrix H. Okay, and okay. Okay, and yeah, well, maybe first I should somewhat motivate why this PI expectation here is natural, right? So in some sense, what we want to prove is that the GII somewhat close to M, right? Or maybe let me write it like this. Is M plus something small, which goes to 0 when n goes to infinity. So that means that we somewhat expect that the left-hand side here becomes deterministic when m becomes very large. And so it's somewhat natural to compute the expectation of the right-hand side here, right? Because, yeah, well, if this becomes deterministic, this right-hand side here also should become deterministic, and then it's, of course, a natural guess that it will be close to its expectation. Well, the expectation of the HII we can forget, right? That's 0. Z is a constant, so that's clear. And then we have to compute the expectation of this expression here. And here there's some interesting observation, namely the h's. So here is always an hi and the h something I. So these h's are independent of the gi here, because the gi is the right the gi was the resolvent of the hi. So yeah, this hi doesn't see these entries here of the h, so these are independent. So if I use the conditional expectation with respect to hi, then this here will actually be measurable, while these here will be independent. So it's very easy to compute this expectation, and that will actually also give you the right answer, because of course it's somewhat natural to assume that if the g becomes deterministic, also this gi should become deterministic in the limit when the n becomes very large. Okay, so and for that we will need these resolvent identities which we had in lemma 16. So let's go through it. So what we want to compute now is the conditional probability of this term here. So that's HIK GKLI HLI without I. Okay. And then what do we get here? Well, so first of all, I can pull out this sum. And then this here is also measurable with respect to HI. So I can pull it out of the, so I can pull the probability here. And the G's I can also pull out, right? This is just a multiplication of scalars. But then the HI's, they're independent of the H upper index I. So this then becomes a normal expectation. And then, so the only thing that's somewhat left to compute is this kind of thing here. But that's 0 if the k is different from L, because they're independent. And only if the k is equal to L, then we get the following. We get the expectation of H, ik, for example. And this is 1 over n. Okay, so that means that the sum here will collapse. And I'm left with the 1 over n, so it looks as follows. Sum k without I, and then the only thing that survives is the g k k I. Okay. And well, and then we use these resolvent identities, which looks as follows. So that's where I use the lemma 16. So namely, I will write this as follows. I have a sum 1 over n, a sum gkk minus 1 over n sum over k, and then I get this other combination gik g ki divided by gii. Okay. Yes, and of course I first use this for all k's that are different from I, then I can use this identity, and if the k is equal to I, then these two terms just cancel, so I just added an extra term. But then this here is just the little g by the definition. So 1 over n sum gik gki gii. And then everything that's left was already done here in star. Because now I computed this expectation, so this term here is the ai. Then there is, and then I added and subtracted the 1 minus pi, which comes with a g. So this all follows. So I just enter claim follows from star. Okay. Is this somewhat clear? Okay, I'll make some space. Well, maybe this I shouldn't have removed. Yeah, well, I want to look at this again. Okay, so this was now some kind of preliminary. So this somewhat gives some hint how we want to prove that the diagonal terms are close to the m. And yeah, I just want to give you some very rough idea of the general approach that we will use to prove proposition 20. Approach of the proof of proposition 20. Maybe some of these words will not mean too much now, but I guess this will be clear in 1 or 2 weeks. So the whole proof is a multiscale argument because we will start from very large eta, which somewhat mean that if you can prove some estimate like this for very large eta, this somewhat means that on this size of an eta window you can understand the eigenvalues. And then we will successively reduce the size of eta, and that's what's called bootstrapping. So bootstrapping from large, so eta was the imaginary part of the z, so we will start with some eta which is somewhat bigger than 1, and then we will successively decrease the eta and keep on proving this estimate for smaller eta to smaller eta. And then there's what's called a bootstrapping hypothesis. And that will be that, so the bootstrapping hypothesis will be phi equal to 1, where the phi is a characteristic function, and it's a characteristic function that describes the event that lambda is smaller than n to the minus tau over 10. Okay? And then, so the idea will be that you first prove this here for large, this kind of estimate for large eta. And then you can use that the lambda is Lipschitz continuous, this we've already seen in some exercise. And then you can somewhat go down to a little bit smaller eta. But then, of course, the error term will be much worse. But the error term should still be as good as this error term here. So we still want to be able to prove with the Lipschitz continuity that the lambda is smaller than the n to the minus tau over 10. And then we want to use this argument again on the new eta to prove that it's actually much smaller, so that it's actually on this size. So this is somewhat the philosophy, and this will hopefully become clear during the next the next 1 or 2 lectures. And so that means that all of the following results will first be on the event where the phi is 1. So that somewhat means that the lambda is not too big. And then in the final step, we'll always have to prove that actually this event occurs at a certain eta. Okay? And the first statement of this type will actually be the following lemma 22, which says that if the phi is actually 1, then the entries of my resolvent are already bounded, and also the diagonal terms are bounded from below. Okay, so lemma 22. We fix a p, and then we have the following estimate. So if I look at phi times a resolvent entry gij, or maybe leave a little bit of space here, then this is stochastically dominated by 1. So that means that, all resolvent entries are bounded. And now the important thing is that should hold for all z. So you might remember that we proved that the gij is always smaller than 1 over eta in the exercises. And actually, in fact, this is also a sharp bound. So if at the real part of your z, the gij really has an eigenvalue, then in general it will also blow up like this. But this statement here says something stronger, because here we will be able to go with the z all the way down to 1 over n, say. So this should actually be of size n, but actually this says that on this scale it's already bounded. That somewhat means that the eigenvalues are not too close to each other, and this spreads more. But this statement here is a bit stronger, because we also get this for minors, and we get that the diagonal terms are also bounded from below. So gij t, absolute value, and this holds uniformly for I and j that are not in the set T, which is a subset of n. And the only restriction we have is that the T cannot be too big. So of course, if you remove too many entries, then this cannot be true. So the P has to be a fixed bounded constant. And the proof will actually be an exercise on the sheet we will post next, the homework for next week. And well, I just give you some small hint. So this is an exercise, and one will proceed by induction on P. Induction on P. And of course, we will use, you somewhat have to use that you have the phi here. So that means that, you have to use that you're close to the m. And about the m we knew quite a bit. and that was recorded in lemma 15. And of course, then if you play around with these sets T, then you of course also have to use these resolvence identities, in particular the first part of lemma 16. Okay. And so that's a very helpful ingredient, and it will be in particular helpful for the next lemma, or in the proof of the next lemma, and this will be the main estimates, and they will tell us that if we are on the event where the phi is equal to 1, so where the lambda is bounded, then first of all, then we will be able to prove that the error terms which appeared in lemma 21 in this resolvent identity, that these error terms are small, and the same holds also true if the eta is very large. So what does the statement look like? So for any z in S, we have the following two estimates. So we have that phi plus the characteristic function where the eta is bigger than 1 times the following, so times lambda star plus the error term ai plus error term zi. This is stochastically dominated by psi theta. And then we have something very similar, or well, no, we have the same bound on the following term, namely if the diagonal entry GII is close to the average of the diagonal terms, and that's also with the same error term. Okay, maybe I should say a few words about this. So how should you read this? So first of all, we can maybe forget for the moment about the phi. So then what does this statement say? Well, if I don't have the phi here, it says that if my eta is bigger than 1, then the lambda star is small. And what does it mean? So that means that the off-diagonal terms are all small. But then it also says if the eta is big, then the error terms ai and zi are all small. Right? So the psi theta, well, what does it look like? It was m plus g minus m over n eta. Maybe that's important. And yeah, the lambda star. Remember, these were the off-diagonal terms. So that's what I just said. So and of course, this here will be small, right? This has a n eta, and this here will also be small. So this gives you that the off-diagonal terms are small and these error terms are small. So that was for large eta, and the same holds true if the phi is 1, right? So as soon as you know that you're on the event where the lambda is not too big, so namely where the lambda is smaller than this n to the minus tau over 10, then you have the same estimate. Then you know that the off-diagonal terms are small and these two error terms are small. Okay? And then the second estimate says that for the same possibility, so either if the eta is large or if the phi is 1, we know that each diagonal term GII is close to the average of the diagonal terms. Okay? And yeah, maybe that's a good time for a break before we go into the proof of this lemma. And so we resume it at 10:15. Okay, then maybe we can restart. So I just added here this definition. So we had the phi, which was the characteristic function that the lambda is somewhat a bit small. Then we had this error term ai, and then we also had this error term zi, which now I wrote in a little bit different form. And now what we will do in the rest of the lecture is we will want to prove this lemma 23. So that means we have to estimate all of these various terms. And we will start with the first estimate here. And for the moment, we will forget about this characteristic function and just focus on what phi times all of these three terms, how we can prove that those are smaller than than the psi theta. Okay, so now we come to the proof. And yeah, let's begin with one of the terms. And let's begin with the phi zi. And yeah, so I wrote down the for now most useful form of the zi here. So it has two terms, and we will estimate them separately. So we just use the triangle inequality to get the following. This one looks like a term as follows. So it's a sum k over I, hik absolute value squared minus 1 over n, g kki plus, and then phi times the sum, and then the usual combination hik gkli hli. And now I noticed that, of course, I forgot the without I here. Okay. And yeah, so this I want to call 1, and this I'll call 2, and we separate them differently. So for 1, we use corollary 19i with the following choices. So xk, the random variables are the hik squared minus 1 over n. Of course, they're centered, and because the moments of the h are bounded, also all moments here are bounded. And then the coefficients, so the ak, this we'll choose as follows. This we'll choose as g kki over n. And then from this we can conclude that we have the following estimate, namely I is stochastically dominated by phi times 1 over n squared, sum over k, without I, g k k I absolute value squared to the 1/2. Okay. And now, of course, we can also pull the phi inside the parentheses, and then we can use the lemma 22 to estimate all of these terms. And then that looks as follows. So that means that all of these terms here are bounded, right? We just use the first one with I and j being k, and the t being I. So all of them are bounded. We have n of them, so 1 n cancels. So this here is just dominated by phi n to the minus 1/2 by lemma 22. And then we can use that this is stochastically dominated by the psi theta, or even with the phi. And here we use lemma 15. And how do we do it here? Well, lemma 15 says that the imaginary part of m is bigger than eta. And so that means that this first term here is bigger than a constant times. This implies that the phi theta is bigger than n to the minus 1/2, and there's a big constant here. Okay, so this we will use quite often. This follows from, so this is lemma 15. There's maybe a small constant here, and then we get this estimate. So whenever we see an n to the minus 1/2, then we're happy, because then we already get that the psi theta as an upper bound. Okay, so that was the first term, and then we continue with the second one. So The second one goes completely analogous, or almost analogously. We just use a different part of this corollary 19. So we use the third part. So, and now we choose the xk as follows. It's the square root n hki. And then there were some b's, and the bkl we choose as gk kli divided by n. Of course, you can always convince yourself that these are independent of each other, right? There's always this argument that here I see an hi, an entry in the I throw, and here I have a gi, and the same here. Okay, so they are always independent, so all assumptions are satisfied. And so we choose these, and in that case we obtain the following. So the second part is stochastically dominated by phi times KLI 1 over n squared GKLI absolute value squared to the 1/2. Okay, and now we use this lemma that if I sum up these squares of the g's over one index, so that was this Watt identity, then I can actually rewrite this as an imaginary part. So this is lemma 17 for hi. So this looks as follows. So we can get the phi. Then inside we can get rid of the sum over L. So it's a 1 over n squared as before. Then we have to pay a price, namely we get a 1 over eta. But we gain something because one of the sum goes away. So we get a gkki to the 1/2. Okay, now I of course need more space. Well, maybe I can try to include it here. So, and now we want to get rid of the I upstairs, and we do this as follows. Namely, we now use lemma 16i, and well, lemma 15 and lemma 22 to get the following. So we get that phi, then we have a sum over k, imaginary part gkk. So this is this first part. So whenever I have an I here, I can remove the I, but then I get two off-diagonal terms, which I will estimate here by the lambda star squared. The n squared eta stays. And then here the k didn't run over I. So so if I add this here, then I get a 1 over n squared eta, and the 1/2 is still there. Okay. Well, maybe I try to keep these definitions, but yeah, well, with the z we are done. So keep these definitions here, and then I just collect the terms. So then this here does not depend on k anymore. I can sum up the k, then I get the imaginary part of the little g, and I have to get rid of one n here, and so this equals to phi times imaginary part of g plus lambda star squared. And then there's this 1 over n term here. And eta, and there's still a 1/2. And then I can use, Then here I can smuggle in an m, so I can write this as an imaginary part of m plus, and then I get the G minus M. So I can estimate this here by 2 times phi psi theta. And then what's still left is the lambda star. Okay, so that's, well, maybe I should mark this so the im G is smaller than im M plus G minus M. Okay, so from this we conclude that phi Zi stochastically dominated by phi times psi theta plus lambda star. Okay. The next thing we have to estimate is the phi AI. Well, what did that look like? This was this term here, so I multiply with the phi. So first of all, upstairs you see that upstairs you see that there are only off-diagonal terms appearing. Now I'm confused. Well, there's one diagonal term which comes with the 1 over n. So there are only off-diagonal terms and one diagonal term which just comes with the 1 over n. And from the lemma 22, we know that this 1 over gii is always bounded. So we can estimate this here as 1 over n plus lambda star squared. Okay. And well, well, we'll now have to estimate the lambda star, but then we will see that this 1 over n is of course affordable. And then what is missing is the lambda star, or phi. Well, of course, I can keep the phi here. And then the lambda star is already small because of the phi. So this is smaller than 1 over n plus phi lambda star. Right? So the square here is actually smaller than the lambda star itself. So what remains is to estimate the phi lambda star. And so we now estimate the off-diagonal terms. And for that we use the second part of lemma 16. We use it twice to get the following relation. So Gij is the same as Gii sum over k Hik Gjki. So that was the first application of lemma 16.2. And now I have to separate one term, so I can write it as follows: Gij Gjji plus sum over k, and now I don't sum over I and j, Hij Kji, and then I can use the lemma 16.2 another time to get the following: Gii Gjji upstairs minus Hij plus sum over k and l, Ij Hik Gkl Ij upstairs HLJ. Okay. And now the first term is again easy. That will be n to the minus 1 half. And then for the second term, we again use our large deviation bounds in corollary 19. Yeah, okay, I need more space. Okay. So now we also use the second part of corollary 19. Now the x case are those guys, y case are the other ones, k, j, and the bkl are the resolvents, so bkli over n. Okay, this gives with lemma 22, it gives the following. So phi times gij, stochastically dominated. So as I said before, for the hij we get the n to the minus 1/2. Then we get a, from the corollary 19, we get a 1 over n squared, sum kl without I and j, gkl ij squared to the 1/2. Then we use lemma 17, so that was the Ward identity for h ij. The first term stays the same. Then I get a 1 over n squared. From the Ward identity I get an eta, k l I j, and I have the imaginary part g k k I j to the 1/2. Okay, and now we do the same game as before. We add the, well, we go back to the GKK without anything upstairs. So we have to use this lemma 16 again. So lemma 16, first part, we get phi n to the minus 1/2 plus, where am I here? Sum over k, imaginary part g k k, plus then something that's of the order lambda star squared, and the whole thing is divided by n squared eta squared, and there's a 1/2 here. Okay, and now I put these things together, so here I again see the little g and the phi, and then I get the psi theta in the same way as before. So this is smaller than lemma 15 to compensate for this term. Psi theta plus something which is of the order phi times n to the minus 1/2, n eta to the minus 1/2 lambda star. Okay, and so now we can take a maximum over I and j to get the lambda star there as well. So take maximum over I j and use a union bound, right? To we can take the maximum, but then we want to pull the maximum inside of the stochastic domination, so we have to do a union bound. But these are just n squared events. This is not a problem. For the n squared error events. And then we conclude from this that phi lambda star stochastically dominated by phi psi theta plus phi times well, we can now use the lower bound on the eta to estimate this term here. So we get an n to the minus tau over 4 times lambda star. And well, now you have some interesting situations. So you have a random variable here that's stochastically dominated by random variable plus something which is n to the, say, minus delta times the original random variable on the left-hand side. And actually what we'll see in the exercises that this term here you can incorporate into the other side, so that you see that this random variable is already stochastically dominated by this without this here, right? You can think of this in such a way that if you would have here an inequality, say A is smaller or equal than B plus, say, 1/2 A, then of course this 1/2 you could bring to the other side, subtract it, then you get a 1/2 here, and so you lose a 2. But some bounds like this, the stochastic domination, of course, doesn't lose this because this is all covered in the n to the epsilon factors here. So we'll see this next week then in the exercises, or you can think about it till then. In either way, this implies then an exercise. This implies that the phi lambda star stochastically dominated by phi psi theta. And then if we combine all the things we've seen before, we have proved a big part of the lemma, namely we've proved that phi times lambda star plus ai plus zi. So if you put everything together, you see that this is stochastically dominated by psi theta. Okay. So that proved, well, the first part of the lemma. And actually, we don't want, I will not go through the proof of the other case because that's actually very similar. Because what did we use in the proof of this estimate? Well, we always use these resolvent identities and large deviation bounds, which are of course also correct without the phi here. And the only place where we really used the phi was this lemma 22, which gave us that this entries gij and the 1 over gii that they are bounded, stochastically dominated by 1, right? That was the lemma 22, and that was the only place where we needed the phi. But these things are also correct without the phi. Just the eta has to be big enough, and eta being bigger than 1 is sufficient. So what did I say? So for the proof of the following estimate, namely the characteristic function that, so when the eta is bigger than 1, we have the same bound. And the proof of is almost identical using the trivial bound GIIT smaller than 1. That comes from this bound with the 1 over eta, which I stated here before. Instead of lemma 22. Okay. So that somewhat proved the first part of the lemma. So then we are almost done. So finally, what is left is to prove that phi, if the phi is 1 or eta is bigger than 1, then we want to prove that the GII is close to little g up to an error of this psi theta. And there we use lemma 21. To obtain the following. The following computation. So the same event as before, we have the following. We can compare the 1 over GII and the 1 over GJJ. And then if you look at the lemma 21, you can easily read off from this that this difference here is the same as well, I think there should be smaller equal here. Yi plus yj. Okay, and as we've seen before, this here is of course stochastically dominated by by psi theta. Okay. And now what we will do is we will rewrite we can just now sum up over over j, and then it will be there after the following step, namely by lemma 22 or that this is smaller than 1 over eta, we conclude the following. Phi times the characteristic function that eta is bigger than 1 GII minus GJJ is stochastically dominated by this. So how do we do that? Well, you just, if you bring both here to the common denominator and compute the difference, then you see that there are some GII, GJJ appearing, but this we can estimate by lemma 22 or this bound here. So we get this estimate, and then one can just sum up, and the claim follows by averaging over j. Well, since, how do we do it? So we have this characteristic function, and then what you want to estimate is this difference here. But now this has this 1 over n sum over j, but this you can also smuggle in here. So you can estimate this trivially by 1 over n sum over j phi 1. And this is stochastically dominated by psi theta. Okay? And that means that we have proved lemma 23, which were the main auxiliary estimates. And this we will then use in the next lecture to do the bootstrapping and then to prove the weak local law. And yeah, then we can stop here a bit early today. And then maybe we start with the exercise classes already at 11, and then I'll say a few things about the last exercise sheets, or we can also discuss some questions if you have them. Okay, then see you later and then next week for the next lecture.